Hey everyone. Thanks for joining. My name is Gunjan Patel. I'm a cloud architect at Palo Alto Networks. And I have been working on containers, Kubernetes as a developer and architect for the last 4.5 years. And with me I have Ivan.
Ivan Boyer. I'm also in cloud architecture in Palo Alto Networks, been dealing with the cloud for probably 7-8 years now. So Gunjan, I really thought that moving our app to the cloud is going to solve our security problems.
It's not, it doesn't work like that. You have to refactor them to microservice architecture, and it takes time.
Just put it in containers.
It doesn't work like that. You can't just say a technical word and expect them to be fixing your problems.
Kubernetes.
All right. So Ivan is also my boss in real life. And this presentation is also to how you talk to your boss and explain them what these technologies are, starting from basics. And then we'll show you some security recommendations on how to secure all these cloud-native different architectures. So concept-wise, this is explaining you the concepts using emojis, right? Initially, you have this software. This floppy represents your software. You hire a bunch of developers, QA, bunch of ops people to deploy it. As the time goes and your application grows, you have to hire more developers, you have more features, more ops people to manage it, right? It doesn't scale, catches fire one day. So someone, some time ago, maybe 10, 15 years ago, suggested that we use a different architecture where we break it down into smaller services that have clear boundaries and specialized concerns. This way, you can also have your individual smaller services written in their own languages. So if a team feels comfortable using a different language for their service, they can write it in that language. You should also be able to feed that team with 2 pies of pizza. It's also called the 2-pizza team. And they communicate to each other over a well-defined standard interface like REST, gRPC, HTTP-based networks interfaces. So the second one, this design is called microservice architecture. The first one you saw that caught fire, that was the monolith architecture. So there was a new concept with the evolution of cloud computing where this is good, but to enhance it, there's also some services that are not always on. So let's take this service as an example, the Python service. It's, let's say, an email service or something that doesn't always need to be running. So you turn it off. When another service says, hey, I need you, it wakes up, starts, does its thing, and then dies or goes to sleep. So you're only paying for that service while it's running. That last one is called the serverless architecture. So using a food analogy might help since our session is right before lunch. And apologies if you feel hungry after this slide. So I want to use three different analogies. One is home-cooked meal. Second one is meal kit delivery. So meal kit delivery is something like Blue Apron or HelloFresh, where they deliver box to your house, which has prepackaged things like this is how much spices you will need, this is how much salt you will need, pepper, these are the vegetables you need. All you need to do is cut things. They'll also send you a recipe and put it in microwave or something. And the last one is ordering food from, I don't know, Pizza Hut or something. So as you move from left to right, there's more work on the left side because you're cooking at home. You have to do everything from scratch. Go grocery shopping, buy food, clean it, decide what to make, and then it's also very time consuming. As you move to the right, it's less work. All you have to do is log into the app and order the food. But it's not very customizable. On the left side, home cooked meal is also very error prone because you're doing everything from scratch. And if you're a bad cook like myself, there's a very high chances you'll mess up. Versus on the right side, if you're ordering from a pizza chain, they have that perfected. They have the art of making pizza perfected, hopefully. So driving the customization point, what if you wanted to try calling Domino's or Pizza Hut and ask them to put some popcorn on your pizza? They can do that, but I can. And I actually did here. So that suggests that like customization is possible with some of the things, some of these. But if you want to over-customize, it's not possible with the last option. So I want to use this analogy for monolith, microservices, and serverless architecture. Quickly, what are container? So container is kind of how you package things. Well, how many of you are familiar with containers? Okay, all right, so about 70% of you. So it's basically pre-packaging all of your code, some of the configuration that's needed for running that code, dependencies and runtime into one package. So you can run it across platform, you can run it anywhere, and you don't see the problem saying it works on my machine and not yours. A good comparison is virtual machines versus containers. Containers are very lightweight because they share the host kernel. This is what also makes them very portable and fast because they don't need to carry the whole kernel with them. Very quickly, what is serverless? So serverless has three pieces. One is events. Second one is function. So first one, event, is the trigger. What triggers your function? Because as I said, serverless means it's usually not always running. When something happens, it will run this code and then do something else, and then it dies. So a trigger could be HTTP or some state change in some data store like S3 bucket or something, or some event happening in PubSub. And then function is your code. You provide your cloud provider your code or a container that they need to run when this event happens. It could be Python, Node.js, Java, Go, whatever your cloud provider provides. A lot of these cloud providers also provide serverless containers where you can just provide them your container and they'll run it. And actions resource is what this function, when it's running, will do. It will store the result into something, or it will trigger some other event that starts another chain reaction, starts another serverless function. So let's take an example of a service called Word to PDF service. You have web front end, people can upload their Word file, and then it converts it to PDF, right? You don't always need that service running all the time. When somebody uploads it, you run this converter, and then you go to sleep. So you click on upload, it uploads that Word file to S3 bucket, for example. you have a trigger that says if something is uploaded to this path in S3, call this function. So you have some Python code that converts that Word file to PDF. It runs, it will do the thing, and it will store the resulting PDF into a different S3 bucket, for example. So this is an example of serverless. Doesn't need to always run, but when it does, it's trigger-based. So why are we talking about these things? What's one of the core problems it's solving? Why are we talking about serverless and containers? So previously, you used to have bare metal or virtual machine. You have your software, RPM packages, or Java, jar files. Your developers are writing code for this time, but this is your overall time, right? This is how long it takes your product team to start coding and ultimately deliver the product. A lot of this time goes into setting up this environment after you write the code, how you're deploying it, optimizing it, managing dependencies, all that stuff. So all this time you're spending that's not writing code is it's not optimized, right? You're not making money for the company. So then came along Docker, which made containers very easy to consume. So next thing you do is duct tape, the container duct tape solution. You take your existing application, which was deployed as VM or RPM packages, just put it inside a container. This kind of optimizes your time. So your developers are spending less time, and ops teams spending less time with managing dependencies, fighting fires, and more time actually automating writing code. And the last one is what we're suggesting, containers and serverless architecture using some orchestrator like Kubernetes, where you maximize your time to write code. Ultimately, this comes down to make better use of developers' time, make better use of ops team's time. And ultimately, this is saving money, right? You can iterate through your code fast, and you can have more releases, you can add more features, and be more productive. So landscape-wise, technology-wise, so far we talked about three concepts, right? Monolith, microservices, and serverless, three architecture, three concepts. Where do technologies stand? So if you look at cloud providers, going from this side, monolith, to left. Sorry, I still get confused left and right because it's behind me. You have, so I'll use Google and AWS as an example. For monolith, you have Compute Engine and EC2. For microservices, Google has Kubernetes Engine, and Amazon has two services, ECS and EKS. EKS is their hosted Kubernetes service. As you move to the right of the spectrum, towards more serverless, there is something called pure serverless, or also known as function as a service, where you just upload your code, and they will take care of your runtime, how you deploy it, how to scale it, etc. Which is the extreme end, which Google calls Google Cloud Functions, and AWS has AWS Lambda. Something in the middle between hosted Kubernetes, hosted containers, and ultimate function as a service is called serverless containers. Google has a new service called Google Cloud Run, and App Engine has a new flavor called App Engine Flex. And Amazon has Fargate, where you just upload your container and then specify a trigger, and they will start the container, do the thing, and then goes to sleep or dies. So overall, I categorize it into four concrete categories: virtual machines, Kubernetes, container platform, serverless containers, and function as a service. Very short description, when to use which technology. So you ask yourself this question, and if you're moving your existing architecture, your existing apps to cloud, VMs are a good start. Customized microservices, where you need to build some complex architecture. Containers are a very good starting point, Kubernetes platform. And if you're writing a website backend or a mobile app backend, your serverless containers are a very good option there. And if you're writing something that's task-oriented, if this happens, then do this small task and then die, then use function as a service. Abstraction also changes from moving from this side to this side. With virtual machines, you're thinking in terms of CPU, memory, resources, load balancing. As you move to containers, Kubernetes, you're thinking in terms of services, connections, state. With serverless containers, you're thinking in terms of request, flow, and your code execution. And on this side, on your right side, you're thinking in terms of function, task, and events. So a couple of things, like what is, so this is, again, you're making a custom meal, right? If you need more customization, you use things that are on the left side of the spectrum, right? Higher customizations with VMs, containers, Kubernetes platform, because these things are less opinionated. As you move to this side, they're more opinionated, less flexibility. One thing to think about is also vendor lock-in. If you're using virtual machines, Kubernetes containers, it's easy to move from one cloud to another without getting locked into a specific cloud vendor. With function as a service, you're more likely to use cloud provider services and will require more changes. Now talking about the shift, how things are shifting. A lot of people like to use this analogy or this example where you had on-prem servers, virtual machines, it's moving to thousands of containers, and which results in lots of tiny functions. But it's not really like that. It's usually a combination of the middle two, right? You're using containers and function as a service or serverless in a combination, moving from monoliths to microservice architecture. And I'll show you with an example how that happens. So you have this service example called Corp. It's an e-commerce website. They have these high-level components in their website called front-end service, where requests come in. Then you have card service, which is basically payment service, which needs to talk to a SQL database called which has customer information and product catalog. Then there's a product service, which has the catalog of all the products. And then you have a support service. So on the website, you can go and if you have a problem with your delivery, you can open a support request or chat with an associate. And there's another database, which is a NoSQL document database, where this support service talks to. There's also an email service, which is a software as a service. We are not maintaining it, but it's a third-party, let's say Zendesk or something. So when somebody opens a support request, it goes and stores it in the NoSQL database and shoots off an email to the customer. Right? At a high level, this is our architecture. So let's go through the iteration. Refactored. First iteration, refactored using containers and microservices. So first thing you do is figure out which components. First of all, you break it down into microservices, which we already did in the previous one, right? We already had separate concerns. Now, and then next thing you do is figure out which of these services can scale horizontally, right? If more requests come in, you don't need to keep adding more CPU and RAM. You can you make another copy and send half of the request to this copy? That's horizontal scaling. If you can do that, that means it's a perfect candidate for containerizing. So you take front-end, card service, product service, and support service. You figure out that all of these don't have a lot of state, right? The state is stored in the database. That means you can scale them horizontally, so you containerize them. So let's say it's Black Friday, or your website goes viral. You start getting a lot of requests. Your card service, your product service will automatically scale, make hundreds of copies of itself, and distribute the request between those copies. And then another thing is your database. SQL database has state. It's not ideal for to be containerizing it. You can, but it's tricky. Containers are originally made for stateless applications. So next iteration, now you try to figure out which components are not always needed. So you analyze your time and see how long each of your services are running, and figure out that not a lot of people are opening support requests, right? It's only like a couple of times a day. It's a small website. So you don't need to keep paying for a support service container to be always running. So that's a good candidate for using serverless. So you put that code in, let's say, Google Cloud Run or Cloud Functions or Lambda or Fargate, one of those containerization or serverless systems that you feel comfortable with. And you have a trigger where when somebody clicks on support, it puts something in PubSub, and it triggers this function. It will retrieve the customer information from SQL database and put the support request body to the NoSQL database and call the email service to shoot off an email, and then it dies. So this is how you can iterate through and figure out which components can be containerized and which components can utilize serverless systems. So next, Ivan, he's also a security expert, and he will talk about how to secure these different architectures.
All right. So I said just put it in containers, right? So now you have a monolith application which you re-architected into microservices. You deploy this to the cloud of your choice, and they're going to take care of security for you. So we all go home, we sleep, I send a bottle of wine to my CISO, and life is great. No, of course not. That's why I still have a job. Security problems are still there, although they're different. And they're different because cloud introduces something called shared responsibility. So if you look at these columns, we kind of try to split them, and leftmost column tries to follow OCI model somewhat. And this is sort of your data center, your own data center on-prem, where you have all these components that you have to manage and secure yourself. As you're moving to the cloud and deploying virtual machines into the cloud, your responsibility changes. Now, you don't get to you don't have to deal with the hardware, physical hardware, which CSPs will take care of for you. You don't have to care about patching OS, because they'll do it for you. But there's still a bunch of stuff that you need to work with them about. This is what they call shared responsibility. Networking and all the above layers, layer 7s. You move furthermore into the future, and now there is a managed Kubernetes clusters, GKE, EKS, as Gunjan mentioned. Well, things become even easier, right? Now they will orchestrate this for you. You know, something that on the left side would be a guy who brings appliance to the data center, plugs into the network, and comes back 4 years later when the refresh cycles happens. Well, they'll take care of for you that through orchestration. all the way to the serverless, where really the focus that you got to put on is really on the code and libraries. So the little square on the bottom kind of shows you sort of what were the traditional security controls that you have to deal with, but you sort of have to relearn and in a way change the culture where you can actually look into topmost in serverless technologies. And I'll explain you why is that important. In serverless, in general, there are three things that are main areas that you care about. One is the code pipeline, your CI/CD pipeline. So everybody that wants to play in this space better make sure that your CI/CD pipeline is secure, modern, and makes sense. For example, CI/CD pipelines is nothing new. We've been doing it for many, many years. But through serverless and microservices, you need to assure that your CI/CD pipeline has security as one of the stages. And we'll talk about how you can achieve some of that stuff. This is what we call sort of shift left movement. Runtime doesn't change. You had to deal with it before. You have to still deal with it. Things like a network, things like different exploits. And then environment itself is more of the physical nature, which you might not have to deal with unless you have something that's deployed on-prem, unless something that's your own, right? Usually CSPs will take care of that for you. But these are pretty much three main sort of buckets of concern as far as security goes in a serverless world. So now, one thing which is sort of a little bit mistaken, serverless is not replacement for containers. Serverless is just another paradigm how you deploy microservices. We at Palo Alto believe that serverless and containers will stick around for a long time, together in unison. Gunjan mentioned that in, for instance, AWS, serverless implementation of the AWS Lambda is with containers. So just to make sure, it doesn't replace containers. It augments them. But the interesting problem as far as the security is that as you deploy your serverless functions, they're kind of, out of your sight. What I mean by that is that you will create a function, deploy it, and you're like, well, it all works. I really don't have to worry about things. Well, and that's where lots of mistakes happen. The orange line kind of represents sort of the a boundary between, like in AWS, for instance, where sort of you have no control over any of that stuff. This is something that AWS Amazon will take care of for you. However, you still need to worry about entire boundary out of it. So another way to say this is that your users still need to get to your application. You got to worry about that identity. Your source code, got to worry about developers. So you got to do dynamic and static inspection of the code. And there are dependencies. The libraries that you use in your code can be third party, can be your own, but you have no idea what's going on there. So all that is something that you got to make sure that it's secure and that it's kosher. It's not that we haven't been doing this before, but with the shift left movement, this is really the main concern. Why do we call it this shift left, actually? I don't really know. I mean, it can be shift right as far as I'm concerned. But the point is that you catch all the potential exploits and CVEs before you actually deliver code to your production. This is really the point where it's the cheapest to capture those, obviously, instead of trying to patch your code in production. Or if you get exploited down the line, obviously, the impact to the company can be just tremendous. In a way, the way kind of following the simpleton way how managers explain this, I guess, is that you have a bank, and you want to put money into the bank, and you don't really care how does bank secure your money. It's FDIC insured. We don't care what happens. But you do have to care about money itself. You got to make sure that you cover the PIN when you go to ATM. You got to make sure you don't lose your card. Well, that's what serverless is for you. So in a way, the good thing about serverless is that the attack surface kind of narrows down. But there are still people who will try to go around it. So you can't completely just get rid of it. You got to actually be smarter about how do you look at a parameter. And there are multiple ways how you can do this. Like I said, CI/CD pipelines. We'll bring your DevOps guys, your security folks at the same table. And they usually don't like to talk to each other. But they will, through utilization of the microservices. And they're going to form something called DevSecOps. You'll have to deal about the exploit management. You'll have to use automated tools that can scan code in libraries. Again, nothing new. We've done this before, but now this is must-have for anybody that's playing this space. Like I said, the parameter changes, but a good thing about serverless is that they are very atomic little functions. So really, you should be able to assure that those functions do exactly what they're supposed to do. So it's not big monolithic code. Much easier to look through the code. You got to document that code, and you got to make sure that you grant the least permissions to these functions. And we've seen through sort of our experience that lots of these don't happen because out of sight, out of mind, like I said at the beginning. You deploy the function, seems like it works, game over. Well, unless you do all of this, it will be really game over for you.
All right, so thanks everyone for explaining serverless security. Now we'll talk about container security, which is everything Ivan said all applies to container security, plus there's more stuff to it, right? So before we jump into container security, it's kind of important to explain what goes into a container image. What is an image? So usually you have a container image where you have your application or function packaged. And every image has a bunch of layers, right? Typically, you have a base layer, which has your base operating system, Ubuntu, CentOS, or more famous recently is Alpine Linux, very small footprint operating system. Then you have your runtime dependencies, language runtimes, Ruby, JVM, or whatever you need for Python. Third-party libraries and third-party code dependencies like NPM packages, if you're running Python pip packages, which is basically OPC, what I like to call other people's code. And then at the very end, you have your code and configuration, which is what your in-house developer writes, right? So, which is just the tip of the iceberg. If you think that securing that is enough, think about all the other layers. Like the big part of your container image is coming from someone else. You don't know who wrote this. You don't know who implemented these libraries. Could be malicious, could have a lot of vulnerabilities. So anyway, when it comes to container security, image security is very important, and you always have to keep this in mind, that a lot of things are not by your own developers. So I kind of want to spend some time explaining the attack surface, and then I'll talk about some specific recommendations on how to secure those areas. Before I get started with this, I want to tell you a story about a electric car maker in San Francisco Bay Area, if you know who I'm talking about. Tesla. So they had their Kubernetes cluster used for crypto mining a couple years ago. And we found that they were getting crypto-jacked. So what happened with Tesla was they were using Kubernetes, open source. It had a package called Kubernetes Dashboard, which is what you deploy to for the UI, how to access your Kubernetes cluster. By default, it has no password. And it's a service, so it's open to the world. It has a public IP. You can reach there and then look at your containers, manage them. It was open, so hackers found that. They had some pods that were doing some storage-related stuff. So it had credentials for their S3 bucket and their corporate AWS account. Now, hackers found a jackpot. They used that to crypto mine in their AWS account. For how long, I don't know. Nobody knows. But they were crypto mining. They were pretty smart about that, right? So through Kubernetes, they figured out their cloud providers' credential. They get into the cloud providers, and they were crypto mining. They made sure they use CPU. They keep the CPU utilization for Bitcoin mining very low, under the radar. So a lot of the security software doesn't create a trigger. They were, instead of using a crypto mining public IP pool, they were using a private pool for crypto mining. So it was going to a private IP, some range that was not listed. A lot of security software works like this. They know known crypto mining pools and their IPs. If it goes there, that means it's bad. They were using a non-standard port for sending those requests. They were also using, Cloudflare provides a free certificate service. They were using that and reverse proxy provided by them. So it doesn't trigger an alert saying this, the traffic was going encrypted, so it couldn't be inspected to see what kind of traffic it is. Non-standard port and through proxy, and an unlisted crypto mining pool. This is how they kept under the radar without noticing anything, and they were crypto mining on Tesla's AWS account, and then until Palo Alto Networks research team figured it out and told them. So that's a story to illustrate. There's a lot of, with customization, as I was talking about on the left side, with more customization, there's also more areas where you can mess things up. So let's use this as a typical environment. So you have your developer writing code that goes to a CI for continuous integration, where you're pulling in third-party dependencies. As I said, a lot of your stuff is not written by your developer. It comes from the internet. Third-party dependencies come in, builds, run some tests. Hopefully you're doing some security scanning here. It goes into a container registry where you store your container images. And for your deployment, you have your cloud provider, which is, let's say you're using a hosted Kubernetes service. They have your Kubernetes control plane. On each node, Kubernetes node, where your actual containers, pods are deployed. You have a Kubernetes component called kubelet. Then you have Docker or some sort of container runtime, which is managing containers. And you have Kubernetes pods, different pods running on the same host, and they share the host kernel to go out to the internet. So first, attack surface is your developer's laptop. You write some code. You don't know. They're using some base OS, so larger the base OS, more the attack surface, right? That's why it is recommended that you use micro OSs, like Alpine Linux, for example. Next one is pulling in third-party dependencies. Again, you don't know who wrote that. Could have a lot of vulnerabilities. Your CI build server, Jenkins or whatever CI you're using, that could get hacked, and people could use that. Your container registry, so where you store your images as well as how you pull your images. You could be pulling some container images from a public repository that are not authorized, right? Then how you're accessing your cloud provider or Kubernetes platform, your SRE DevOps team, so your IAM and RBAC. Then Kubernetes control plane. Typically, if you're using hosted Kubernetes service, it's managed by your cloud provider. Again, on the host, kubelet could be compromised. It could be misconfigured. Docker itself, Docker's socket, anyone could talk to it and then hijack Docker. That means you basically own all the containers running there. Pod itself, where your containers are running. So if pod gets compromised and it's a privileged container, it has access to your host kernel, and it could in fact affect all the containers on that host. Then you have pod-to-pod east-west network security, and then north-south, your containers to the internet. So these are all the attack surfaces. And if you need high-level recommendations, I have a GitHub repo where I list all the different areas and what steps you need to take to secure those. And again, another thing that a lot of people forget is also the cloud provider. Like in Tesla's case, using Kubernetes, they've figured out how to access their cloud provider and Bitcoin mine there, so securing those. At a high levels, Kubernetes security, these are the 7 areas that you need to think about. And these are, again, very high-level recommendations. I have another repo for cloud-native security that has very specific implementation suggestions with risk score. So image security, make sure you do scanning, scan your images, use binary auth or some sort of authorization to pull those images. For network east-west, container-to-container traffic, make sure there's network policies or Istio application layer policies that say this app is allowed to talk to this app on HTTP GET. It can only do HTTP GET, not POST and PUT. So you can get very specific like that. Using service mesh, you can have MTLS, encrypted traffic between your containers. North-south traffic coming from the internet going out, make sure that's also firewalled. Isolation, proper use of Kubernetes namespaces. A lot of people put all of their stuff into the default namespace. Make sure it's properly architected because there's a lot of concepts that built on top of namespaces, security concepts. Making sure there's no privileged containers unless absolutely needed. Shared mount, network, and IPC namespaces. Again, running in a container doesn't mean it will give you isolation. You have to make sure none of these things happen to get proper isolation. As well as registry isolation. So you have your separate container registry for dev, staging, and prod, and a proper way to promote an image to production one. Data security, secrets, config management, and storage security. Again, I have more specific recommendations in the other repo. Environment, securing the environment. Make sure your OS is hardened. Google COS, for example, it doesn't allow you to execute anything. You can only run containers there. And it's a read-only file system. Using some sandboxing technologies like gvisor from Google, Kata containers, Nabla containers, SE Linux to limit the surface, what syscalls you're allowing, what's going to the actual kernel because it's shared. Access management, making sure who has what access, what cloud resources, as well as Kubernetes, RBAC. Kubernetes also has role-based access control, where which service account, which users, which groups have access to which of the Kubernetes resources, and what actions they can take. Make sure you have those policies specified. And last one is behavior security. So monitoring processes to see what are all the system calls they're making, what network ports they're calling, monitoring the process or container overall. And another big recommendation is making your container file system read-only. With Kubernetes, you can do that easily with security context. But a lot of things, when they're running in your environment, they'll download something malicious from the internet, download it, and then execute it. So if you make it read-only file system, most of the Metasploit exploits won't work if it's a read-only file system. This is a reference architecture on how you can secure the whole thing, from code pipeline to registry to runtime. So starting on your left side, this is why it's called shift left, by the way, because people like to imagine left side is where you write the code. I don't know. So we have ISE scan service, free public API from Prisma Cloud. You can scan Kubernetes manifest, your Terraform files, your CFT files for security issues, right? Kubernetes allows you to do all these things. Doesn't mean they're all secure, right? So it will find those issues and give you a verdict. You can have a policy that says, if the overall risk score is higher than this, then fail the build. See, this is a good thing about everything as code. Your infrastructure, your network policies in Kubernetes, everything is as code. So you can run a lot of automated checks and fail the CI if there's anything that's against your policies. Next thing you do is image scan. Again, Prisma Cloud, this is also known as Twistlock. You can scan your container images after they're built to see your code, your dependencies, OS, if it has some vulnerabilities. You can have a policy that says if there's more than 0 critical vulnerabilities into this image, then fail the CI build. If there's more than one high severity CVE that has a fix, then fail the build. Ultimately, if that all goes well, you check in your code to GitHub or Bitbucket, your manifest to the same repo, and store your images to container registry. To get into the production, or staging Kubernetes cluster, make sure there's very few people. Ideally, no one should have manual access to that Kubernetes cluster. Only your CD deployment pipeline should have access to it. But in there, you need east-west network security between container to container traffic, going from either one host to other host or on the same host between the two containers, going out to the internet. Again, same thing, you have Twistlock that can help you secure this conversation, as well as VM series for traffic that's going out to the internet or coming in from the internet. This is where you can also use runtime and behavior security provided by Twistlock, which learns how your application is supposed to behave. And if anything suspicious happens, I'll show you in a demo. It will flag it. It can also block it. Another thing that needs to change with this is process, right? When you were writing monolith applications, you had your developers working in isolation, and your ops team, InfoSec team is creating infrastructure, making sure they use a secure environment. And then during your deployment time comes your production day. That's when they meet for the first time, and that's when they're supposed to, that's when they figure things out, like, okay, we have these issues. But now, with everything as code, your security as code, your Kubernetes deployment, all of that as code, you need to start working from day one. When developers writing their Docker file, which specifies what packages are going in, your InfoSec team, your security team tells them these are the only allowed base OSs. You can pull packages from here. You put security controls in the CI pipeline, so before the code even makes it to GitHub, you're running all these checks. So it's a smoother deployment. When you're deploying the application, it's a lot smoother. So in conclusion, These are the 4 different technologies that we talked about, 4 different concrete technologies. They have their own use cases. You're thinking of different abstractions for all these different technologies. And security, in terms of security, you're also thinking of different things when it comes to securing these infrastructures. For example, virtual machines, you're thinking of securing the OS, code vulnerability, environment, pipeline, runtime, behavior security, and network security. With containers, it's container images, runtime, networking, and isolating the containers. For serverless containers, it's pretty much the same as Kubernetes containers, but less worrying about the infrastructure because cloud provider is managing that. And last one, function as a service. All of it is in your code. The example Ivan used was bank. It's like using strong password for your bank. If you use ABC123, regardless of how many security checks your bank has, people are going to hack into your bank and get all the money. I want to quickly show you a demo of this. So this is Twistlock UI. So I'm going to show you three things. Twistlock can do more things, but I'm just showing you a couple of things here. So this one is vulnerability management. When you scan your container images from your CI/CD pipeline, or at the end you're scanning your registry continuously, it will find all these CVEs, vulnerabilities. You can go and look at. It will give you a reference to the actual CVE. Then you can also look at image view. So you click on an image, container image, and it will give you a list of all the vulnerabilities that are there in that container image. You can click on one of the CVEs, and then it can also show you what are the attack vectors, like what is the actual impact. You can also narrow it down by has fix. So this is really bad, right? This CVE has a fix, but it's not fixed. It's still there. That means you can have some sort of policy that says if it's a high severity CVE and has fix, developer must fix it before pushing it into production. Layers, as I explained, every container image has a bunch of layers. You can see which layer has all these vulnerabilities. You can break it down by different layers. This is why one of the recommendations, if you visit the GitHub link, is also using fewer layers. Compile your code into a binary and use a basic Scratch image or Alpine Linux, very small distro, so your image is a few megabytes. That way you're limiting the attack surface. Then this can also show you which processes are run, how this process is getting called. Now moving on to behavior security. This is called the radar view. It will show you which containers are talking to which other containers. And red color here shows more vulnerabilities. So you zoom into this red one, it shows you it has 3 incidents. And here you can see, so the way Twistlock Twistlock works is when you deploy the app, you can have a learning phase. It uses some machine learning to monitor how your application behaves, what system call it's making, which network ports it's calling out to, a lot of other stuff. And then if the behavior deviates from that, it can create an alert or it can block it or quarantine. So in this one, it says there was a weird file system access. Sorry, the brightness is very low and I can't increase it. But yeah, it's basically doing a webget call to download something from the internet and it's executing it at the local file system. Oops, sorry. then you can see it will show you the impacted assets, where this container is running, which host, which Kubernetes pod, and which images are in fact, which image has this exploit running. So, and it also shows you the vectors, process, and network. It's also calling out to some strange port. So it's looking at all those things. And the last one we'll look at is serverless security. So as I explained in my slide about serverless, this view has the same identical three things. There's an event, trigger, your code, and then the resource it's modifying. So same three columns here. So in this case, it's the AWS API gateway. You can click on it, and it will show you what are all the triggers that are calling these Lambda functions or Fargate things. You can look at the actual function, and it will show you what permissions it has and what are the triggers, how this function gets called. And the last thing is what resources it's operating on. So this one is working with CloudWatch logs and what permissions it has. So if you look at this and figure out that it doesn't need to do certain things with CloudWatch, why does it still have access to those things? You can figure that out, narrow it down. Red color here also means that this serverless function is not scanned by Twistlock. It's not just container images, it's also the your serverless functions. And you can easily do one click and it will automatically scan your code that's running in Lambda. That protect button right there. It shows that it's not protected by Twistlock. And okay. That's weird. Can you turn on this thing? That doesn't work. I'll just use my slide then. With that, you have these resources, and this is our contact information. We don't have time for Q&A, but we'll hang around if you have any questions. So, thank you.
Thanks.